Hello, my name is Josh. If you don't know, I go to Penn State. And what I did this summer was I studied the effects of pickup ions on magnetic reconnection in the heliosheath. So first, the process. So magnetic reconnection is a physical process that occurs whenever two oppositely oriented magnetic fields meet. And they meet at this X point that you'll see right now on the slide. It meets at that X point, and then new magnetic field lines are created. And these magnetic field lines naturally want to snap back to straight. Whenever these field lines snap back to being straight, they drag along any particles that are captured along with them. Now, we see this occur across the universe, from solar flares and coronal mass ejections in the sun to auroras on this planet and other planets, and even in the most extreme places in the universe, like neutron stars. Now, where I studied it this summer is in the heliosphere. The heliosphere, at about 120 times the distance between the Earth and the sun, is where the solar wind plasma that comes out of the sun blows out an edge, a little bubble for our solar system against the interstellar gas. Now, because this is a very chaotic system and a very big system, it's really hard to simulate. And now the players in the system are the pickup ions. These are created in, they're created in the heliosphere whenever a solar wind ion collides with an interstellar medium, stripping away the electron from the interstellar medium neutral hydrogen atom, taking it away, leaving this newly made ion to get picked up by the magnetic field, the local magnetic field. So now, from observations from spacecraft like Cassini and New Horizons, we know that they're an energetically important component of the heliosphere. We also know that comparatively to other ions, they're numerically a numerically small component. And so this summer, I studied how the energies of these pickup ions affect the process of reconnection in the heliosphere. So as you can see on screen right now, this is a magnetohydrodynamic simulation. The colors show the relative strength of the magnetic field, and you can also see the black magnetic field lines. MHD simulations are really great at simulating larger scale physics. Unfortunately, they get the smaller scale physics right. As you can see around here, it's a little bit darker. And we know that magnetic reconnection occurs around here. And again, MHD doesn't do that smaller scale physics that well. That's where my project this summer came in. I used what is called a particle in cell code, which is exactly as it sounds. This is a distribution of randomized thermal ions and electrons. And I, along with the help of Mark Swizdak, my mentor, we recreated very similar conditions in the heliosphere, similar conditions to what we find in the heliosphere. So the simulation is basically this box, and in the heliosphere, we get magnetic field lines going back and forth constantly. And so this creates a movement of current, and that current is represented by the white going out of the page and the black going into the page. So next, you'll be seeing a video of the reconnection actually happening in my simulation. So as you can see, those lines start getting pinched a little bit. And then as the simulation continues, you start seeing bubbles form, and then more interaction occurs until you get this very nice ending here where you see a lot of interaction occurring between the different bubbles. Beat that, Christopher Nolan. So what I did was I ran 4 different runs. Vmod represents the speed of the pickup ions, which is how I added energy to these pickup ions to test reconnection. As you can see, there's visibly noticeable difference in the amount of reconnection that occurs in each of these simulations by the end of the same amount of time. And you can especially see this between our two more extreme cases, Vmod 8 being a much more energetic distribution compared to Vmod 2. Now, to help kind of quantify and try to see what's happening to the reconnection itself from these distributions, we looked at 2 different things, or I looked at 2 different things. First, the fire hose instability. This occurs in electrically conductive plasma, where essentially the thermal energy in the plasma takes over and the magnetic field lines doesn't do much with the plasma. And what happens to the process of magnetic reconnection itself is that those field lines that you saw in the very beginning animation don't snap back. So then that process of reconnection starts slowing down and even stopping. So for the fire hose instability, we defined a parameter called beta, which is the thermal pressure over the magnetic pressure. And whenever beta parallel to the magnetic field minus beta perpendicular to the magnetic field is over 2, we get a plasma that is unstable to the fire hose instability. So what you see here is the number of grid points in the simulation that are unstable to fire hose over the time of the simulation. And as you can see, very interestingly, they're pretty close. So that is a very interesting question to investigate that we'll talk a little bit later on. A second thing that we looked at was what's essentially the net angle in the box of the magnetic field. So these are taken at the very end of each simulation. And again, I plotted the number of grid points on the y-axis. And what happens throughout reconnection is that the magnetic fields start changing, and then the angles start becoming more randomized compared to these peaks that you see on screen here. VMod 2 that we saw earlier had much more reconnection. You can visibly see that it's much flatter and starting to randomize more compared to the other more energetic distributions. So again, we do see that reconnection is slowed by more energetic pickup ions, but it's also interesting to see that the number of fire hose unstable points is very similar across the different runs. So for future work, it would be very interesting. One of the very interesting things would be investigating why fire hose in different pickup ion distributions don't change. And then, of course, we can also run the simulations longer and at higher resolution in order to see more of what happens in the process. We can add much more of a variation in the distribution of pickup ions to more accurately simulate what happens in the heliosphere. We can also test this with newer hybrid simulations that take the best of MHD and PIC codes. I'd like to thank Daniel Serrano, PhD, for making this all possible. And I'd also like to thank Mark Swizzak for being an amazing mentor and a great teacher. Thank you.